It speaks not only of enhancing communications, but also of disrupting them. Not only of atmospheric study, but also of atmospheric control. Whether these capabilities were ever fully realized remains uncertain, but the potential envisioned in the patent was vast and ambitious, and in many respects ahead of its time. As the high-frequency active aurora research program became operational, a number of public outreach efforts were made to frame its purpose in purely scientific terms. Tours were offered, academic collaborations were initiated, and data was published. Nevertheless, the shadow cast by Eastland's original invention remained. The notion that a system had been proposed decades earlier which could potentially affect everything from radio communications to climate patterns ensured that the project would never be entirely free of scrutiny. Even today, with the original military-run version of the project having been transferred to a civilian research institution, the theories and fears associated with Eastland's patent endured. Much of his persistence is due to the sheer breadth of his claims and the openness with which they were presented. Unlike classified documents or covert programs, this patent was a public document available to anyone willing to read it. That openness has made it a cornerstone in the architecture of both legitimate inquiry and less grounded speculation. In a broader sense, the legacy of the patent reflects a recurring theme in modern technology or technological history: the convergence of military ambition, corporate resources, and scientific vision. The invention was not the product of an isolated genius working in obscurity, but of a deliberate effort by a large energy company to repurpose its assets in a way that might influence the skies themselves. Whether that influence was intended to be benign or strategic remains an open question, but the implications of the work are clear. The apparatus described in Eastland's patent envisioned a world where upper atmosphere could be shaped like clay on a potter's wheel, subject to the invisible hand of electromagnetic force. It imagined a future in which human beings standing on the ground could reach up into the charged layers of the sky and alter their behavior for communication, defense, or possibly environmental purposes. That vision, while never fully realized in the precise terms described in the patent, nonetheless set the stage for one of the most enigmatic and debated scientific installations of the modern era. The concept of the magnetic monopole occupies a unique place in the history of science, straddling the boundaries between theoretic physics and experimental pursuit. It is, in its simplest form, a magnetic monopole is a particle or object that possesses a net magnetic charge, meaning it would act like an isolated North Pole or an isolated South Pole. In contrast to every magnet observed in nature, which always has both the North and South Pole, regardless of how finely it is divided. A magnetic monopole would be a singular source, or sink, of magnetic field lines. Though never observed in nature, the idea of such an entity has persisted through generations of scientific thought, fueled by the elegance it brings to the mathematical frameworks that describe the physical world. Excuse me. Magnetism, as commonly understood, arises from the movement of electric charges and the alignment of microscopic magnetic movements in materials. Ordinary bar magnets owe their properties to the spin of electrons and the arrangement of atoms in ferromagnetic substances. When a magnet is cut in half, the result is not a separation of poles, but the creation of two smaller magnets, each with its own north and south pole. This fundamental symmetry has led to a widely accepted belief that magnetic dipoles are inseparable. Yet the theoretical possibilities of breaking this symmetry and finding a genuine monopole remains one of the most enticing quests in modern physics. The origin of the idea stretches back to the early 19th century, when scientists began developing the field theories of electromagnetism. The Scottish physicist James Clerk Maxwell formulated a set of equations that described the behavior of electric and magnetic fields. These equations contain a notable asymmetry. While electric charges exist in positive and negative forms, there are no corresponding magnetic charge in his model. Magnetic fields always arise from currents or dipoles, never from isolated monopoles. Maxwell himself acknowledged this imbalance and speculated whether a magnetic charge might someday be discovered. However, the idea remained dormant until the early 20th century. It was in the early 1930s that the concept of the magnetic monopole received a profound theoretical foundation through the work of British physicist Paul Dirac. He showed that if a magnetic monopole existed anywhere in the universe, it would explain the otherwise mysterious phenomena of charge quantization. In simple terms, all observed electric charges are exact multiples of a fundamental unit, such as the charge of an electron. Dirac demonstrated that the existence of even a single magnetic monopole would require this quantization as a natural sequence of quantum mechanics. This insight not only restored symmetry to Maxwell's equations, but elevated the search for monopoles from a speculative notion to a matter of deep physical significance. Despite the elegance of Dirac's theory, the decades that followed yielded no direct evidence of magnetic monopoles. Experimental physicists searched high and low, from the depths of particle accelerators to the analysis of moon rocks and meteorites. Some detectors were constructed specifically to spot the characteristic magnetic signatures that a monopole would produce as it passed through matter. Though a few anomalies were reported, none proved conclusive, and the existence of the magnetic monopoles remained unconfirmed. In the meantime, theoretical development continued to lend support to the possibility of monopoles. In the later half of the 20th century, efforts to unify the fundamental forces of nature, particularly the electromagnetic, weak nuclear, and strong nuclear interactions, led to a family of models known as grand unified theories. These models predict that at extremely high energies, such as those present in the first instance after the Big Bang, the distant forces merge into a single interaction. Crucially, these theories also imply the spontaneous formation of magnetic monopoles during symmetry, breaking phase transitions in the early universe. According to these models, magnetic monopoles would be extremely massive, far heavier than any known particle. Their density should have been significant in the early universe, yet today they appear to be absent. This inconsistency is known as the monopole problem. To resolve it, cosmologists proposed the theory of cosmic inflation. In this scenario, the universe underwent an exponential expansion within a tiny fraction of a second after its birth. This inflationary burst would have diluted the density of monopoles to a level where they would be exceedingly rare today, so rare that none may exist within the observable universe. In more recent years, interests in magnetic monopoles have resurfaced in an unexpected place.